Today's lesson, lesson 2, is looking at finding limits analytically using algebraic approaches. First, we're going to review some theorems or properties of finding limits. And we're talking about the general limit of some function f of x and some function g of x. So both of those limits will exist, and the constant rule can be applied. So the constant rule says the limit of a constant is equal to that constant. In other words, if you have a horizontal line, say y equals 3, y equals 3 is a constant. So the limit at any value along that line is just going to be the constant 3. And the identity rule says the limit as x approaches c is just going to be the c value. So that's the identity function, y equals x. Then any x value on the line is also going to be the y value. And then the rest of these properties, I'm going to show you my verbal description as we go along. The sum or difference rule. So let's say we have the limit of two functions, f of x and g of x, and we're either adding them or subtracting them. Then you can say that the limit of the sum is the sum of the limits, or the limit of the difference is the difference of the limits. The same goes for the product rule. If we're multiplying two functions, f of x and g of x, and you're looking for the limit of that product, then the limit of the product is the product of the limits. And constant multiple rule, if you have a constant multiplied by a function, then you can take the limit of the function and multiply it by the constant. So the limit of a constant times a function is the constant times the limit of the function. There's the constant multiple rule, the quotient rule, the power rule, and the root rule. Verbally, the quotient rule says the limit of a quotient is the quotient of the limit, provided that the denominator isn't 0. The power rule verbally says the limit of a power is the power of the limit if the exponent is a rational number. The composite function rule says the limit of a composition is the composition of the limits, provided the outside is continuous at the limit of the inside function. This one's a little more complicated, and you see more of that when you explore AP Calculus. And then finally, the root rule. I gave it two different ways. Over here, I said the limit of the root for any number greater than or equal to 2 is going to be a real number, provided that those two exist. Here I said it this way: the limit of a root is the root of the limit, provided that the root exists. So if the root on this right side exists, then that limit property can hold. So let's just explore some of the basic ones. Suppose the limit of f of x is 4 at some target number c, and the limit of g of x is -3, and the limit of h of x is 9. We want to use the properties to find these limits. So in this first case, we can separate them. The limit as x approaches c of f of x plus the limit as x approaches c of g of x. So if this limit is 4, the first one, and the second one is -3, then we have our limit is equal to 1. In this case, we want to bring the constant out front, multiply times the limit as x approaches c of f of x, and then bring the constant out front and multiply as the limit approaches c for g of x. So we have that constant 3 times the limit of f minus 5 times the limit of g, and that should be a minus there. And that's looking like 12 plus 15. So 12 plus 15 is 27. So our limit of that difference is the difference of the limits, and that happens to be 27. Here in this case, we're going to bring the 7 out in front of the limit and take the limit as x approaches c for f of x times the limit as x approaches c for g of x. So where those brackets are, we've got all of that times 7. So 7 times 4 times -3, and 7 times -12 is -84. And then our final example, we want the -6 to be brought out in front of the limit of our numerator, and then divided by our limit at c on the denominator. So that's looking like -6 times +4, and the limit of h of x was 9. So we have -24 divided by 9, and we could get rid of a factor of 3 here. 3 divides 6 2 times, and 3 divides 9 3 times, so -8 over 3 is our limit. On example E, we have the limit. We can take the limit as x approaches c for f of x, and find that limit, and then raise that entire limit to the third power. So the limit of f was 4, and now we can cube that, and our final limit would be 64 in this case. And this one was similar to letter D, so 4 times the limit of h of x, which was 9, divided by the limit of g of x, that was -3, and 36 over -3 gives us a limit of -12. And here we can bring the limit on the inside, so square root of 6 times the limit at c for h of x, and that limit was 9, so 6 times 9 is 54, or we can say the square root of 9 is 3, and 3 square roots of 6 would be our simplest form. And then in this case, again, I'm going to take the limit at c for the numerator and the limit at c for the denominator, and then take the square root of that limit. So this limit was 9, this limit was 4, and the square root of 9 over 4 would be 3 over 2. So just using the basic properties for limits, algebraically separating them. In this example, we're going to look at some more graphic approaches, but we're going to use those properties with the graphic approaches. And a dual page would help us see both things better. So using these graphs, find the limit of f of x plus g of x. And again, I want to think about separating the limit into two separate questions. The limit as x approaches 2 from the left for f of x, and then add the limit as x approaches 2 from the left of g of x. So we've got this graph of f of x. We want to approach 2 from the left. So from the left would be this branch, and we're approaching 2 from the left. It's heading to -1. And then on the g of x graph, we're approaching 2 from the left. So we're heading to 2 from this direction. That would look like 3. So -1 plus 3, our limit is 2. In this case, we're going to use the properties and bring the constant out front. So 2 times the limit as x approaches 1. So we're looking at the general limit in this case. And then we're going to subtract 3 times the limit as x approaches 1 on our g of x graph. So 2 times the limit of f of x at 1. So the left limit and the right limit are both approaching -2 in that case. So we have 2 times -2, and we're subtracting 3 times the limit of g of x at 1. So as we're approaching g at 1, it looks like the limit's going to 2. So we have -3, or subtracting 3 times 2. So -4 minus 6 gives us a limit of -10. Okay, so letter C, same approach. We're looking at the limit, general limit in this case. X approaches -3 for f of x, and we're going to subtract the limit as x approaches -3 for g of x. So the general limit at -3 is +3, and the general limit at -3 on g of x is +4. So 3 minus 4 gives us a limit of -1. So this limit is -1. And then the limit at 2, so we want to take the limit as x approaches 2, the general limit for f of x, and then we'll square that value. So the general limit of f of x at 2 for letter D, we have a problem. So this is our first case where we have a general limit. So what we want to do is first look at the limit as x approaches 2 from the left. So as x approaches 2 from the left, it's going to -1. And we need to square that. That's going to be +1. And then the limit as x approaches 2 from the right of f of x, that looks like it's +1. And then we need to square that. So in order for the general limit to exist, the limit from the left and the limit from the right must be the same value. In this case, they're both +1. So we can say that the limit as x approaches 2 for f of x, quantity squared, will be +1. And like I said, that's the composition, and those are dealt with a little more in depth in an AP Calc class. But we do have to explore the left limit and the right limit. They have to be the same in order for the limit to exist. And then our last two examples, E and F. For E, we're going to look at the limit for g of x, the general limit, as x approaches -3. So we want to multiply -6 times the limit as x approaches -3 on g of x, and then divide that by the limit as x approaches -3 on f of x. And this looks like it's going to be -6 times, let's see, we're approaching -3, times 4, so -24 in the top, and f of x at -3 is +3, so 24 divided by 3 with a negative will give us -8. And our final one is a product, so the limit of the product is the product of the limits. The limit as we approach 3 for f of x is going to be 3. And the limit as we approach 3 for g of x is going to be -2. So 3 times -2 is -6. And there we have the results of the limits using graphs and combining those properties. Letter D was the more complicated of those 6 examples. So here, just cleaning this up, these are our final results here. 2, -10, -1, 1, -8, and -6. Now, the substitution theorem says if f is a polynomial function or a rational function, then the limit as x approaches c of f of x is going to be the function value, provided that f is a rational function, the value of the denominator doesn't equal 0. So we'll see what that's about using substitution. So the first one, by direct substitution, is pretty straightforward. Most of us can do this in our head. We want -1 cubed, and we want to do 2 times -1 squared, and then -5 times -1, and add 4. So we've got -1 plus 2 plus 5 plus 4, and that looks like 10. So by direct substitution on a polynomial, pretty straightforward. Here we have 3 squared minus 6 times 3 plus 5, and then 3 plus 3. So that looks like 9 minus 18 plus 5 divided by 6. So -3. Let's see, what's that? -2/3, I believe, because we got -4 over 6. So -2/3 would be the simplest form. And then here in this case, we've got the square root of 3 times 2 cubed. So that's 8 times 3 minus 2 times 2 plus 5. So we got 8 times 3, that's 24 minus 4 plus 5. So we got the square root of 25, which is 5. And then example 4, the cancellation technique. Sometimes it's necessary to factor and simplify before you can apply the substitution theorem. So here in this case, if you try direct substitution at 2, we're going to end up with 4 plus 2 minus 6 divided by 4 minus 4. And when that works out to indeterminate form, 0 over 0, that's when you know it's necessary to factor and simplify. So when you try direct substitution and get 0 over 0, which we call indeterminate form, that's an indication to try something else. So the something else I would try in this case is to factor the numerator and factor the denominator, hoping that you have some common factor that can be removed. That's where the cancellation technique, that name, comes from. I prefer to say I'm removing a 1, but some people call that cancellation. Then we can try direct substitution. So 2 plus 3 is 5, and 2 plus 2 is 4, and you do have a limit. The graph would have a hole in the graph at 2, and the y value of the hole would be 5 over 4. So 2, 5 over 4 is a removable point discontinuity. You might want to explore that on your own using a graph calculator to see what happens. So I'm just making the assumption that this is also going to be indeterminate form. Let's give it a try to factor, since it's grouped in this lesson about simplifying. So we know 8 times 3 would give us 24, and if they were both negative, it would produce that middle term of 11. And 5 times 3 would give us a 15 if one of them was negative. So the 3 is negative, the 5 is positive. We can definitely take out or remove the x minus 3 factors and then use direct substitution. 3 minus 8 is -5, and 3 plus 5 is 8. So the limit at 3 is negative 5/8. We had a removable discontinuity. In part C, it's going to be the same thing where we've got some removable factor. So looking at the square root after we take these limits, so we got what? X plus 8 times x minus 4. We can take out the x minus 4 common factors. Substitute 4 in there. So the limit as x approaches 4 is 4 plus 8. That's the square root of 12. And the square root of 12 would be 2 square roots of 3. I didn't turn my color back. And then lastly, our limit of the quotient is the quotient of the limits. And again, I'm making that assumption that I'm going to have a removable factor. In this case, it's going to be x minus 3, since the difference of two squares in the bottom and factoring out an x in the numerator gives us that removable factor. So plugging in a 3 here, we have 3 on the top and 6 on the bottom, so our limit is 1/2. That's called the cancellation technique, or factor and simplify. So the rationalization technique, that's the rationalizing the numerator or denominator, and in this case we would want to rationalize the denominator. So our factor would be the square root of x plus 2, and the square root of x plus 2 would be our well-chosen 1, and we can multiply both numerator and denominator by that. That would give us the limit as x approaches 4, and our numerator would be left alone. I'm going to do nothing to the numerator. And the denominator, when you distribute the square root times the square root, we got x, and then inside and outside is going to produce a 0 and then minus 4. So now you can see why I did not distribute the numerator, because I've got that common factor here, which lets us take the limit as x goes to 4 for the square root of x plus 2. So substituting 4 into our x term, we've got the square root of 4 plus 2, which is 2 plus 2, so our general limit is 4. In this case, our rationalizing is going to be to rationalize the numerator. So we want to have a conjugate for x plus 1 for both top and bottom, and then we would use distributive property only on the top, leave the bottom alone, and continue with the limit notation. So our limit as x approaches 0, if you distribute for the first two terms, we're going to end up with an x plus 1, no radical, and then this positive 1 and then this negative 1 term. They cancel, add up to 0, and then minus 1. So our numerator ends up just being an x. There's already an x in the bottom. So thinking about this as combined terms, we've got an x in the top and an x in the bottom. They're gone. And then we've got the square root of x plus 1 quantity, and then add 1 more. So now substituting into that term alone, we've got a 1 in the numerator and a 0 plus 1 plus another 1. So 1, and then the square root of 1 is 1, and 1 plus 1 is 2, so our limit turns out to be 1/2. Now you might want to turn off the camera and try these on your own, and then come back and check with me to see that your work and my work look the same. See you in a minute. Now in the first one on part C, I used the conjugate of the denominator distributed through, and canceled a common factor of x minus 1 from the top and the bottom. That left me with just this term in the top, and I substituted 1 in place of x and got the square root of 4 plus 2, which was 2 plus 2 for 4. But in part D, we used the conjugate of the numerator, distributed the numerator to get x plus 1 minus 4. That allows us to remove the x minus 3 from top and bottom, left a 1 in our numerator, and then substituting 3 into the denominator is the square root of 4 plus 2, so we end up with the limit 1/4. And then our last example is going to be some special trig limits. You might want to memorize these and look at them graphically to verify on a graph that as you approach 0 for sine over an angle is going to be 1, and then that you approach 0 on this function, you get a 0. So using the properties from earlier, we can say 5 times the limit as x approaches pi over 4 for the cosine function. If you think about the cosine function at pi over 4, that's square root of 2 over 2. So 5 times the square root of 2 over 2 is your limit, or you can say 5 radical 2 divided by 2. In this same sense, if you substitute the sign, pull the 7 out in the front and think about the limit as x goes to pi over 2 on the sine function, then you know that the sine at pi over 2 is 1, so 7 times 1 gives us a limit of 7. In C, we have 1, I'm just going to substitute directly here, minus the cosine of pi over 2 divided by pi over 2. So the cosine of pi over 2 is 0, so 1 minus 0 divided by pi over 2 becomes 2 divided by pi. Now this one's a little trickier because we need to have the property look like the rule. So whatever my theta is, this theta must be the same. And we don't have a 4 theta in the top and a 4 theta in the bottom. So what my goal is to get that. And then I can use the property. The only way to get that to happen is to multiply both the top and the bottom by 4 over 4. So I'm going to think about this as 4 over 4 is not changing the problem. It's just getting me what I need to match that property. So the sine of 4 theta divided by 4 theta times this extra 4 here in the numerator. So I can pull this apart and think about the property, the limit as theta goes to 0 of sine of 4 theta over 4 theta times the limit as theta goes to 0 of 4. So this is my rule right here that says this rule goes to 1, and the limit of 4 is 4, so the limit on this one is 4. And then our very last one, we want to think about those properties that we can rewrite tangent as sine divided by cosine. So sine of theta over cosine of theta, and then I can also break this apart to be the limit as theta goes to 0 of 1 over theta to get that denominator. And if we rearrange them, we can break this apart to be the limit as theta goes to 0, and I'm going to put these two together. So the sine of theta over theta, I'm going to put this one, theta, with this numerator, and then bring this one over theta over, goes to 0 of 1 over cosine. So this is the rule here, and that rule is 1. And if you think about 1 over cosine of 0, that's also 1. So 1 times 1 gives us the limit of 1. That's lesson 2. See you next time.